Right, so in this next set of examples, we're going to be focusing on how we can use Venn diagrams when we're working with conditional probabilities and what the conditional probability actually looks like on a Venn diagram. So in this example, C and D are two events such that the probability of C occurring is 0.2, probability of D occurring is 0.6, and the probability of C occurring, given that D occurs, is 0.3. Find the probability of D given C. So the first thing what we want to do is to work out if we have any intersections between the two events C and D. So we're given a conditional probability, so because we're given the probability of C given D, using the conditional probability formula, we know that that is the same as the probability of C and D occurring over the probability of D occurring. Within there, we're given C given D, and we know probability of D, which means that we can work out what the intersection probability of C and D occurring is going to be. So probability of C and D would be probability C given D multiplied by probability of D. C given D is 0.3 and D is 0.6. So probability of C and D occurring will be 0.18. Now if we look at that on a Venn diagram, what that means, we've got event C and event D, and now I know the intersection there is 0.18. If I know the intersection is 0.18 and C in its entirety is 0.2, that means that that must be 0.02. And I know that the probability of D occurring is 0.6, so if the intersection is 0.18, then D, only D occurring, is going to be 0.42, the difference between 0.6 and 0.18. I also know all probability has to sum to 1, so if I take from 1 the 0.02, 0.18 and the 0.42, what's left is the probability of neither occurring. So as soon as I've worked out that intersection, I have enough information to complete that Venn diagram. Okay, so back to the questions. Probability of A, what's the probability of D occurring given that C has occurred? So what that means, looking at the rule, is probability of D and C, which we've just worked out, D and C, C and D, doesn't make any difference to the order, divided by the probability of C, which we're also given. So that's going to be 0.18 out of 0.2. So 0.18 divided by 0.2 is 0.9. On the Venn diagram, the probability of D given C has occurred would be the probability of D occurring when it's inside C, so it's 0.18 over the fact that it's also in C, which is the sum of those two, which is 0.2. So you could figure it just from the Venn diagram, but using the formula is easy enough. B, probability it's not in C and it's not in D. So we practiced those AS Venn diagram work in previous session, so we should be able to figure, or just check back through your notes, that's saying it's not in C and it's not in D, so it's the outside of that, it's the inverse of the union. So we can just write that down from the Venn diagram. And another Venn diagram that we looked at last week is a fairly standard one. It's the probability that it's not in C and is in D. So the probability that it's not in C takes everything outside that circle, but ANDed, it has to be inside D. So that, on our Venn diagram, is this sort of half moon part, not half moon, crescent moon there. So we can again write that straight down. It's that 0.42. So long as we are comfortable with the aspects of a Venn diagram, and we can use our conditional probability rule to work out intersections, this is quite a straightforward thing to work with.